So we've just talked about the idea of a sampling distribution of sample means, and then we've also talked about this idea of a point estimate. So a point estimate is a single number. The sample mean is our single best guess without additional information for the population mean mu. Well, we also have not only point estimates, but we have something called an interval estimate. An interval estimate is sometimes called a confidence interval. What it does is it provides additional information about variability. So we often have a point estimate, sample mean, and then we have sort of a range of plausible values. We have a lower confidence limit and an upper confidence limit. So to understand this concept of an interval estimate, well, let's look at this Iowa census data again. What would happen if each time we calculate a sample mean X bar, we placed upper and lower bounds or limits on a particular point estimate? Right? One approach is just to take each sample mean, our best guess of mu for that particular sample, and set upper and lower bounds based on the standard error of the sample mean. So sigma divided by the square root of n, which tells us how far off we are on average from the population mean mu. So let's look at what we call approximate 95% confidence intervals. We can think of the mean of a random sample as a point estimate for the population mean, mu. Using the concept of the standard error, we can create a confidence interval or an interval estimate. We take our point estimate for a particular sample, and then we add and subtract 2 times the standard error of the sample mean, or 2 times sigma divided by the square root of n. So we're going to refine this in a bit, but this is a great rule of thumb to use. You take a point estimate, plus or minus 2 times the standard error, and you have an interval estimate that we sometimes call a 95% confidence interval. This is what it looks like. So we have a sampling distribution of our sample mean, which here we've modeled as a normal distribution. So we're assuming that we have a sample size of 30 or greater or so, or in the population, the distribution is normal. And here we have about 100 point estimates. Right? These are 100 sample means. So let's suppose we just collected 100 samples of the same size from the population, and for each point estimate, for each sample mean, we add and subtract 2 times the standard error. So in this case, we're just assuming that we know the standard error. We assume we know the population standard deviation. We divide by the square root of n. But the key point is that we have not only 100 point estimates, but we have 100 point estimates plus 2 times the standard error and minus 2 times the standard error. So we have these range of plausible values. Right? We have these interval estimates. And you can see those interval estimates are bouncing around, just like the point estimates bounce around. The key point here is that if you notice, this population mean mu, right, it stays the same. There's one population mean mu, which we don't know. And you can see sometimes those interval estimates, sometimes they include the population mean, and other times they don't, because those population means are bouncing around. But in general, right, because here we're constructing approximate 95% confidence intervals, we'd expect about 95% of these interval estimates to capture the true population mean mu. So you can see we're about 95% of these 100 or so interval estimates or confidence intervals, they contain that true population mean mu, which is denoted by that vertical black line marked by mu. Right? So we might say, the standard error in this case, it's based on sigma divided by the square root of n. We typically don't know the population standard deviation. When you gather a single sample from a population, right, you just have the sample standard deviation. You don't know the population standard deviation. Thus, in practice, we typically use the sample standard deviation S as our best guess for the population standard deviation, sigma, in the same way that we use the sample mean X bar as our single best guess for the population mean mu. For now, we're going to assume that, however, that we know the population standard deviation sigma and that our sample is pretty large, 30 or greater in terms of the number of observations. And thus, we're going to use the normal distribution model. In the coming lectures, we'll see some adjustments we might make when we actually have to guess the population standard deviation using the sample standard deviation S. For now, we're just going to assume that we know the population standard deviation. So let's continue with approximate 95% confidence intervals in which we assume that we know the population standard deviation. We can think of the mean of a random sample as a point estimate for the population mean, and then using the concept of the standard error, we can create a confidence interval or an interval estimate, which again is this point estimate plus or minus 2 times the standard error, where the standard error is sigma divided by the square root of n. This is a very important rule of thumb. It's very useful. Now, one aspect of an interval estimate or confidence interval is that we need to be careful how we interpret the interval. The standard error, it represents a standard deviation associated with the estimate in terms of the sampling distribution. And so with an interval estimate, we will know that roughly 95% of the time the estimate, it's going to be within 2 standard deviations of this unobserved population parameter. So if the interval spreads out 2 standard errors from the point estimate, we could be roughly 95% confident that we have captured the true population parameter. So this is very important. What do we mean when we say we have 95% confidence that our interval contains the true population mean? Formally, what this is really saying is that, quote, 95% of samples of this size will produce confidence intervals that capture the true population parameter, the true population mean mu. This is a bit long-winded, so often people will say, as shorthand, they'll say, we're 95% confident that the true parameter lies in our interval, where the interval is the point estimate plus or minus 2 times the standard error. Again, the key point is that some of our confidence intervals, they're going to capture the true population mean, which is given by that vertical line, and others won't. Right? Some intervals won't contain the true population parameter. But since in practice we just have one sample mean and one interval estimate, we don't actually know whether our particular interval contains a true population parameter or not. We're just 95% confident that it contains a true population parameter. But in practice, it does or it doesn't. Right? So you can see here, there are a couple intervals that actually don't contain mu, but most of them do. That's what we mean by 95% confidence. Right? We're 95% confident that the interval contains the true population parameter. That's because our confidence is in the process of constructing the interval, not in any one interval itself, because any given interval either does or does not contain the true population parameter. So let's look at an example. Let's look at a random sample of runners. Suppose we find that a random sample of runners, and we calculate a sample average of running time of 94 minutes. Right? If the standard error, if sigma divided by the square root of n of our estimate is 1, what is the 95% confidence interval? Well, the 95% confidence interval is just going to be a point estimate plus or minus 2 times the standard error. Here we're given the value of the standard error, which is sigma divided by square root of n, and that value is 1. Right? So we just take our point estimate 94, we subtract 2, and we add 2. So we get this interval estimate based on 92 to 96. So we're 95% confident that the true population mean lies in this interval of 92 to 96. To put another way, about 95% of intervals we'd expect to contain the true population mean if we repeatedly took random samples of the same size from the population, each time calculating a point estimate and calculating plus or minus 2 times the standard error. Right? Of course, our sample could be an odd one. Right? In reality, it's possible that our true population parameter lies outside our interval. Right? But we're 95% confident that the interval contains the true population mean. That's because if we were to collect, say, 100 samples, each time collecting a point estimate, collecting and constructing a 95% confidence interval, about 95% of those intervals would contain the true population mean mu. And with that, we're going to explore a bit more about constructing approximate 95% confidence intervals by taking this point estimate plus or minus 2 times the standard error.